We've already talked about capacitors in series and parallel. We're going to go through the same kind of analysis with resistors now. It's very, very similar.
Is this still correct?
Yeah. It's very similar. Yeah, this is still assignment 3, guys. This is for chapter 28.2, section 28.2. It's a very similar analysis, but obviously a little different result. Let's take a look at the difference between a resistor and a capacitor. If you have a capacitor, okay, could you stop talking, please? Or if you want to talk, you can go outside and sit down. All right, we've got, what you've got, the voltage drop comes because you formed an electric field between these plates. Right? So a battery has been attached and there's no current flowing anymore. We're going to talk about RC circuits later. But for right now, when we deal with capacitors, there's no current flowing through them. But we do have a certain amount of charge here. And we have a certain voltage drop. And it's a voltage drop because, remember, E times D, the electric field, times the distance across the plates gives us the voltage. And since we're going with the electric field, it's a voltage drop. We're losing potential. But in a resistor, oh, and by the way, energy is stored in this electric field. We're storing up energy in the circuit. Now, if I have a resistor, has current flowing through it. So now this has Q, but this has dQ dt, or a rate at which charge is going by. This has a current. And so this current, as it flows through, we get a voltage drop. Now the voltage drop across here, right, delta V equals, Q over C. And here, delta V is equal to I times R. So this has a certain resistance. This is a certain capacitance. This is a certain resistance. And so there you go. So current is the important thing here, where charge was the important thing with the capacitor. So let's take a look at two resistors in a circuit that are in series. Let's put a battery in there. Now we just talked about internal resistance and all that. That's about the only time I'm going to talk about internal resistance. We're going to assume from now on that the internal resistance is negligible. Why? Just to make things easier. Okay?
Is that a permanent thing or just a discrete thing?
Well, like on the test, there will be a problem with internal resistance. I want to see if you can understand it. But all the other problems, nah.
Okay.
So we'll call this R1 and R2. This could be two Christmas tree lights you wire together. Now these are resistors in series. Now they're in series because they share the voltage and the current has only one path. There's only one path through them. So here's my my delta V, and I'll call this the terminal voltage, so we kind of like say, well, the given voltage here is already compensated for the internal resistance. And so we're going to go through here, and we're going to have a voltage drop and a voltage drop to get back to 0. So delta V, that is the voltage gain I get from this battery. Think about voltage, man. Whoop. You gain voltage, you come around here, mew, mew. Okay, you're going to jump down. You have 2 jumps to get back to 0. So the voltage gain, then you have minus I times R1 That's the voltage drop across here, minus I times R2, and that will equal 0. Well, let's rewrite this. This is the voltage drop due to 1. This is the voltage drop due to 2. Put them on the other side, and you get this. The voltage gain from the battery has to be equal to the 2 voltage drops. Deltas are kind of a pain, but I'll go ahead and write them. Delta V1 plus delta V2. So the voltages add together. This was the same, by the way, for capacitors, wasn't it? When they were in series, the voltages added. Whoa. Now, but what's the same? What is the same for the resistors? What's the same for R1 and for R2? The current flowing through them. Well, remember when these were capacitors, it was the charge that was the same. But we're dealing with resistors here, so they have current flowing through them. But look, they're in series. They have to have the same charge flowing through them. They have the same current. So the total current delivered to the circuit is equal to the current flowing through this one, and it's equal to the current flowing through this one. Okay. Now I can use these ideas now to come up with the what is the resistance of the total circuit? What's the equivalent resistance of these 2 resistors? Okay. So what we'll do is we'll take this one right here. Well, let's see. Delta V. Well, the total voltage for the whole circuit is equal to the current times the total resistance for the circuit, or the equivalent resistance. So delta V is equal to I times the equivalent resistance. And that's going to be equal to delta V1, but that's I R1, or I1 R1 plus I2 R2. That is the voltage drop across there. But of course, what's true about all these currents? They are the same, so you divide by them. You cancel them out, and you get the equation for the equivalent resistance. Plus R2. And by the way, it was just arbitrary. What if I put 3 resistors in there? Well, you would just have a plus delta V3 up here, but I3 would be equal. You just put a plus I3, and you'd end up with a plus R3 down here, plus dot 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 plus Rn. However many resistors you have in series. Yes.
I have a really dumb question.
No.
For when you're doing R equals R1 plus R2, is it wrong to say R total instead, or why is it R? Is that
Well,
R2 or?
Okay. Yes. For this circuit right here, when you break these down into and add them together, let's say this was 20 ohms and this was 30 ohms, you'd add them, you get 50 ohms. That's the equivalent of these 2. It's also the total resistance for that circuit.
It's equivalent, not.
Right.
Okay.
Now in a complex circuit, I would break 2 down, but there's other resistors, and so we're going to do that a little bit. So this is an equation that you should write down on your equation list for resistors in series. They just add. Now, by the way, this is different, isn't it, than capacitors. Capacitors, you had 1 over the equivalent capacitance is equal to 1 over C1 plus 1 over C2, etc. And look, that's because delta V is equal to Q over C, where the voltage drop, that's because the voltage drop is Q over C, wherefore the way we define resistance, delta V is equal to I times R, not divided by R. Now let's talk about resistors in parallel. Well, here's my battery delivering voltage to my circuit. Here's R1, here's R2. Now, I bet you could do this on your own quite easily, because I think you're really getting a good sense of the ideas here. What's the same for R1 and R2? The voltage drop. Voltage man whoop, comes up here. Oh, this is all at high volts, but I drop down here, I lose it all. 0 volts. Or I can drop up 0 volts. Same voltage drop. So delta V total is equal to delta V1 is equal to delta V2. So the voltage drops are now the same. That's what defines two circuit elements that are in parallel. They have the same voltage drop, which means you have two paths. Now, let's talk about current. Here's I. That's the total current delivered to the circuit. Here's I1, and here's I2. Well, what do you think? I1 and I2 better add up to I. Conservation of charge. You can't just create current out of nothing. So this is called a junction right here, and the amount of charge that goes in has to be equal to the amount of charge that comes out. So I is equal to I1 plus I2. Well, delta V equals IR. So the current is equal to delta V over R. So this is the total current, which means it's equal to the total voltage divided by the total or equivalent resistance. And that's going to be equal to I1. But I1 is going to be delta V1 over R1 plus, and I2 is going to be delta V2 over R2. But the voltage delivered is equal to the voltage on the two resistors. In other words, delta V and delta V1 and delta V2 are all the same. So what happens to them? They cancel out. And so you're left with this equation. 1 over the equivalent, or the total resistance for the circuit, is equal to 1 over R1 plus 1 over R2 plus plus 1 over Rn. If you have n, I could have a whole bunch of resistors in parallel here. And this is what you use. Okay, now here are the big ideas that you need to use to solve these circuit problems. And they're very similar to the capacitor problems that we've done. And they can be just as irritating. First of all, resistors in series have the same current, but they split up the voltage drops. Where resistors in parallel have the same voltage drop, but they split up the current. Using those two ideas and the fact that the voltage drop across a resistor is equal to the current times its resistance, you can solve circuits. And solving circuits means you know what all the currents are, you know what all the resistances are, you know how much energy is going out, I squared R and all that. So now it's just a matter of practicing it with a bunch of problems. So good luck with that.